looks something like this. Okay? So with radius, with respect to radius, of course. So we know our Coulomb force. VC R is about, or rather our Coulomb potential is 1 over R. Okay? So that's, so you can divide this into 2 sections. So here we have the Coulomb, right, dominates here, and over here is nuclear force dominance. So this is what I was talking about a little bit ago. If I took a proton out at infinity and tried to bring it into the nucleus, I would start seeing this potential slope, which of course generates a force going in the other direction. So I run into more and more and more force, and then I get over this hill and thunk, that falls right into the nucleus. The strong nuclear force takes over strong nuclear. Okay. So imagine we've got a higher energy state and a lower energy state. Okay. Inside the nucleus, the wave function of this alpha particle, or soon to be alpha particle, 2 protons and 2 neutrons planning a prison break, it's going to look a little something like this, and then decay through there, and then we can escape. And then we have something that's more or less like a plane wave, right? After these particles, so this would be maybe the second harmonic here, or whichever harmonic, and then has some decay as it goes through the potential barrier, and then on the other side, it can escape as a free particle, as a plane wave, essentially. Okay. And then we have some lower energy state. It also has some probability to escape, but the amplitude outside of the potential barrier is much smaller, right? Still have this plane wave wiggling out to freedom and infinity. But of course, since I had to tunnel through more and more of this barrier, right, because we're in a lower state, we're going to escape with a lower amount of energy, which means that higher energy states have a higher probability of escaping the potential well, and lower energy states have a lower probability of escaping the potential well, and that is borne out in experiments. Okay? So that's just the first part of the 3 types of decay. The next is the gamma particle. And the gamma particle, I'm not going to talk about too much. It's fairly intuitive. I keep checking the time. That's why I'm not just like squinting at your. What are you doing over there in your house? No, I'm not squinting at you. I'm squinting at the time. I'm in your home. I'm sorry. That was really weird. Hey, I've been cooped up in here for weeks with no one to talk to but my cat. You guys should meet my cat. Since we're going to end a little early. Franz Josef, Wacken. Franz Josef, Wacken. Sie müssen meine Studenten treffen. Oh. This is Franz Josef. Oh, he's such a sweet little kitty. Yeah. It's Franz Josef von Habsburg. It's an Austrian cat. Royalty, obviously. Yes. I woke him up, so now he deserves some pets. Okay. Back to physics. gamma decay. Gamma decay is a photon. Okay. So we're accustomed to photon emission absorption when we're talking about the full atom, right? When we're talking about photons, or rather electrons moving up and down in their energy states. As an atom absorbs a photon, the electron moves up to a higher energy state, and as it moves down, it decays to a lower energy state, and it emits some photon off into space. So gamma decay for nuclear states are more or less the same thing, right? Nuclear states are extraordinarily complicated, right? You have however many particles in some weird arrangement under the force of some force that's not very well mapped out. And now he's going to start meowing. I shouldn't have woke him up. The class is almost over. Yeah. What was I saying? So essentially the nucleus can change its internal configuration to move from a higher level energy state to a lower level energy state. And as it does this, it emits a gamma particle, right? The difference is that these gamma particles, these photons, are extremely high energy, in fact quite dangerous. So that's the main difference between photon emission from the nucleus and photon emission from the electron cloud, is that because the differences in these nuclear states are due to differences in the configuration of the strong nuclear force, the most energetic force, to use language loosely, we see that these gamma particles are much more energetic, okay? And in fact, quite dangerous, can damage your DNA, etc., etc. So stay away from them. In fact, very high energy electromagnetic radiation, regardless of origin, is called gamma rays, right? Whether it comes from a nuclear transition or not, it's just, if you drew out the electromagnetic spectrum, there's gamma rays is the most energetic side of it, right? Okay. So, after a gamma particle is emitted, the nucleus hasn't lost any particles. So it's not like an alpha decay where the nucleus is shedding bits of itself. It still has the same number of nucleons afterwards. And this often follows an alpha or beta decay where particles have been lost, and now that nucleus has some particles have flown out, and now the remainder of the nucleus has to fight its way down into its own lowest energy configuration, right, without losing any more particles. So oftentimes there'll be an alpha or beta decay and then a gamma decay following it. Also possible that an electron will be emitted instead, and this is called a conversion electron, right? Okay, and that happens, I think the cartoon for it, and check your book because I'm not totally sure about this, I think the cartoon for it is then the gamma flies off and hits an electron, and then the electron also flies out, okay? All right, next class we will talk about beta decay and start talking about nuclear reactions. Right, so hopefully this format's a little better than the way we have been doing things where you're just watching the back of my hand. Sorry for getting a little weird and showing you my cat, but what can you do? Okay. All right, I hope everyone's staying safe and healthy, and all the best.